Willkommen zu unserer Mini-Reihe Antrittsvorlesungen. Wir hatten schon eine erste Antrittsvorlesung hier in unserem Kanal VP-Uni Brains und ich sagte Ihnen schon damals, dass Sie diese Antrittsvorlesungen natürlich auch live erleben können. Diese Termine entnehmen Sie unserer Website. Heute haben wir hier für Sie die Antrittsvorlesung der Kollegin Frau Prof. Alodie Rey-Mermet in der allgemeinen Psychologie. In diesem Vortrag geht es heute um Attentional Control, more than just task-specific processes. Seien Sie sehr gespannt in diesem auch an der Grundlagenforschung ausgerichteten Beitrag, der spannende Einblicke bringt, wie wir unsere Aufmerksamkeit kontrollieren. Und freuen Sie sich schon auf den nächsten oder auf die nächste Antrittsvorlesung in absehbarer Zeit hier in diesem Kanal. Vielen Dank.
Dank für die nette Einführung, and as I said, I will do it in English. So thank you very much everybody to be here with me for this talk, and as already said, the topic is about attentional control and how can we measure attentional control and what we are measuring in the typical attentional control task. And here I use attentional control in the same way, although at least for the sake of this talk, as cognitive control or executive function for those people who already perhaps know the name. And typically, attentional control is so defined that it refers to our ability to prioritize mental representations that are currently relevant for a goal. Let's be less abstract and take an example. Imagine we are driving home and we see a traffic light. I hope that everybody knows that when the traffic light is red, we have to stop, and when it's green, we can go on, or we can move on. The point is, what happens when we see a nice police officer close to the traffic light? Actually, we will look at the officer and we will prioritize the representation or the information coming from the police officer because they are relevant for us in order to achieve our goal, that is to go safely and surely to home. And we have to ignore the irrelevant information coming now from the traffic light. And actually, attentional control, it is the ability, or it is assumed that this ability allows us to do that. And research on attentional control has, in my opinion, I am sure I am not really objective on this point because I am a researcher on attentional control, but research on this ability has really increased in the last 20 years or 25 years. One reason for that is that actually attentional control has been used as an explanatory construct. For example, it has been used to explain age differences between children or also between older adults and young adults. For example, it has been used to explain why some older adults or why older adults have some deficit in everyday tasks, for example, in comparison with young adults. Another reason or another area in which attentional control has been used is, for example, in psychopathology. For example, it has been used to explain key symptoms or key phenomena or disease of psychopathology. On the other hand, it also be used to explain, for example, the relationship between working memory, also it's the ability that allows us to retain a limited amount of information for a short duration, and intelligence. So we know from a long time now, I will say that people who have a high working memory capacity, meaning that you can retain a lot of number of items, such as, for example, numbers or words or sentences, for example. Such people also have good or very high score on intelligence. And one explanation for that, which has been put forward by some researchers, is that actually the reason is that people have a good attentional control, explaining why they are good at working memory and intelligence tests at the same time. And the question is about this construct is about how can we measure attentional control. And in order that for you it's a little bit clear how we are doing that in the lab, here I present you two types of tasks. The first one is a soup task. I will say that it's the most typical task. Probably most of you know them. In this task, you will see color words, and your task actually is to name the color of the word, but to ignore the word itself. Okay, we will do now some example that you understand that. As usual, in cognitive psychology, we start with a fixation cross in order that you focus your attention on the middle of the screen where the stimulus will appear. and now you will have the first stimulus, and here you see, okay, it's a word blau, which is written in red, and in this case you have to name the color, so it means the correct response will be red, and you have to ignore blue actually. And when you give the response, for example, when you press a key or you name it, we will go to the next trial, also to the next stimulus, also first with a fixation cross, and then you have a second stimulus. And here you can see that we have red in red, and here you have to say, actually, the correct response is red. And we can go on, because the goal is not only to test 2 times, but to test several times across several trials to have this information. Here, for example, the correct color will be, the correct response will be blue. Only that you show how that we have different tasks actually to measure attentional control. I'll present you a second task. It's the flanker task. In this task, you will see a row of characters actually, and the goal is that you name the color of the central character, but you ignore the color of the flanking characters, okay? Again, we will do a few examples that you understand how it works. Again, it begins with a fixation cross. The goal is here that you fixate the middle of the screen, and then the stimulus is coming, and here the correct response will be blue, because you have to ignore the color of the flanking letters. Then when you give the response, a new trial will start, and so on. Here the correct response will be red, and so on. Here the correct response will be red again. And the point is, I think you get it in both the Stroop task and the flanker task, where we had 2 types of trials. We have some trials in which we have congruent information, as for example, when red was presented in red, as here the color as well as the word triggers the same response, red, and they are used as baseline trial. But more interestingly, we have incongruent trials, as here meaning that you have, for example, the word blue printed in red. And here it is assumed that you have a conflict in the case between the two types of information coming from the word or coming from the color. And here it is assumed that you need attentional control to resolve this conflict, to focus on the relevant information, meaning here the color, and to ignore the irrelevant information, meaning here the word. And what we are measuring actually is the time you need to provide a response from the onset of the stimulus on the screen until you give a response either verbally or with a key press. And here I am showing you some results where I get from previous studies. On the left, you have a picture, a figure of typical results. On the y-axis, you have the reaction time. As I said, is the time you need to give a response from the onset of the stimulus until the response. And on the x-axis, you have the 2 types of trial, congruent, which are our baseline, and incongruent, in which we are expecting the impact of attentional control. And what we see is that participants are slowed in incongruent trial compared to congruent trial. And this performance difference, which is sometimes called the Stroop effect or the congruency effect, is taken as a measure of attentional control. Because everything is the same across both congruent and incongruent trial, only in incongruent trial we expect the impact of attentional control. It's a reason why the congruency effect or the Stroop effect is used as a measure of attentional control. And exactly the same is happening for the flanker task. We have also 2 types of trial, and when looking at the results, we see here that participants are slower on incongruent compared to congruent trial, and this performance difference is also taken as a measure of attentional control. And across the year, there were different conceptualization of attentional control. I will say that at the start, attentional control was considered as a unique construct. So you will have one unique construct to all situations you need attentional control. For example, when you are driving home, or when you are now at the moment looking at my slides and perhaps ignoring some disturbing noise coming perhaps from your surrounding. So here, meaning that we have only one using for everything. Across the years and the research, it was shown that actually might be not the case, might be too easy to simplify actually to understand the concept. And the idea that we have was put forward that we have more diversity, meaning that we are more than one unique construct. And the point is that in this diversity, there is diversity as well, meaning that some researchers actually conceptualize the diversity of attentional control in different ways. Also, for example, some researchers have the idea that to have only one big construct as before, but in the case they also have some sub-construct, here displayed or illustrated by the small circles, okay? And because of that, we can have sometimes in some studies the impression that we have only one construct. Others have said, okay, we don't need this big construct, or we only have the sub-construct, but they are related to each other. And thus giving also the impression that we have one unique construct. And still other researchers say, actually, no, we have only the sub-construct, and they are not related to each other. Okay, and there is some debates ongoing which is the best conceptualization. But one assumption which was common across all conceptualization is actually that we are able to measure the control process or the control processes as a sub-construct by at least two different tasks. And the goal of my research and the main question for this talk is to question that. Do we really have converging evidence that show that actually we can measure the same attentional control process using several tasks? And to respond to this research, actually, I use three approaches. I will say the first one, which is really experimental. The second was a meta-analytical approach, and the last one is a combination of experimental and a correlational approaches together. Because of the time, I will not have the time to go in details across all three approaches. I will give a quick overview of the first two, and then I will go a little bit more in depth in the last one. So let's start with the experimental approach. And here the idea is if we are measuring the same attentional control process across two different tasks, we should observe an effect as an interaction in performance. Meaning that when we are resolving a conflict, for example, the Stroop conflict, this should help resolving the flanker conflict and reverse. And to respond to this question, what we did, we combined the attentional control task together. We see the same trial. And it looks like that. We have here one stimulus, and we instruct participants to respond to the color of the central letter, as to this letter. In this case, the correct response would be red. And then in this case, in order to provide this correct response, participants have to ignore the meaning of the word, as white in the case. So it will be the Stroop aspect of the task or the Stroop conflict of the task. And at the same time, participants have to ignore the color of the flanking letters. And so here it will be purple. And in this case, it will be the flanker conflict, but respectively, the flanker aspect of the task. And as said before, if it helps to if we are measuring the same attentional control process across the two tasks, we should see an interaction in performance. It should help when we already resolve one conflict, for example, the flanker conflict. It should help to resolve the Stroop conflict, and we should show that in a way that we are better or we are faster in responding to the stimulus. And when looking at the results, it's exactly what we have. As here on the y-axis, you have the reaction time in milliseconds, and on the x-axis, you have whether the flanker was congruent or incongruent, and the true line, it's a difference, it's a Stroop effect, the difference between Stroop congruent and Stroop incongruent trial. And what we see here, it's an interaction, meaning that the Stroop effect was smaller when the flanker was incongruent compared to when the flanker was congruent. And when looking a little bit deeper, we see that when both stimulus were congruent, so Stroop and flanker, here we see that participants were slightly faster than when the flanker was congruent, but the Stroop was incongruent, so when only one was incongruent. And thus, we speak for the idea that responding to the flanker conflict triggers some attentional control processes or resources that helps you, actually, to respond to the Stroop conflict. But if it's like that, actually, we should see that when we have a better resolution of the time course of the conflict effect. And one great thing is that actually EEG allows us to do that. And we did the same experiment using an EEG. And here I present quickly actually the results. But what we see in the EEG results that we have a flanker effect actually on the EEG as expected. We also have a Stroop effect as expected, but we didn't have this interaction. So meaning that, yes, we had an interaction on the behavioral data using the reaction time, but this interaction does not result actually from the same attentional control process. So when we are coming back to the big question we had here, meaning that actually at the moment it's a little bit disappointing because the experimental approach doesn't allow us to say that we are measuring the same construct. But we are still two possibilities. Let's look now at the meta-analytical approach. And here the idea was to look at the age-related decline across the typical attentional control task using a meta-analysis. And the idea or the assumption behind that was if we are measuring the same attentional control processes across two different tasks or across several different tasks, we should observe a similar age-related decline across these tasks. And to respond to this question, we performed a meta-analysis on the 10 most typical attentional control tasks using about 200 studies. And then we use actually a statistical method that allows us not only to provide evidence for an age-related deficit, but also to provide evidence against such an age-related deficit, or also evidence or even inconclusive evidence showing, for example, that we don't have enough data to say whether we have evidence for or against an age-related decline. And looking directly at the results, what we show actually is the three types of evidence. For some tasks, we had some age-related deficit. For other tasks, we don't have such age-related deficit. And we also have inconclusive evidence as well for some other tasks. So meaning that we found an age-related deficit, but this was not, we don't find a systematic pattern across the task. For example, the first three tasks are in the previous literature assumed to measure the same attentional control process, though we would have expected to find the same kind of result in the case, and here, as you can see, it's not the case. So meaning that, again, regarding our research question is, can we measure the same attentional control process across different tasks? The meta-analytical approach is, again, disappointing because we don't have this evidence so far. But we have still one possibility, one chance, and it's the last combination, or the last approach in which I combine experimental and correlational approach. And here, in this approach, the idea is to look whether we can establish some common ground, some common variance across the different attentional control tasks. Meaning, for example, that if a participant is good, for example, in one task, in the Stroop task, it will be also good in the Flanker task. Okay? And to look at that, first we use the best of the experimental approach, in which we implement the task in a way to remove or to isolate attentional control from all non-attentional control processes and all the measurement error, also the noise that we have in every measure. And then we use structural equation modeling, which is a statistical method that allows us actually to look at these common variants. And now I show you the results. Don't worry, we will go through together. Also here, what is important to see is that on one side, you have the measure as actually what we measure in the lab. And here you can see, for example, it will be the Stroop effect. And we had, for example, two versions here of the Flanker task. And we have here the Flanker effect. On the other side, you have the factor, which is actually the common variance, what we are looking for. But before we can go to the step to respond to the question, here, do we have this common variance? We have a few things to look at. First, we have to look whether the model we have, because here what I present with the idea, we have two factors, and the manifest variable are loading to one factor and not to another, for example, is a model. And we have to fit, also to know whether the model fitted to the data, if we have a match, because it's a good idea, it's good to have a match. If not, we have a problem because we are not corresponding to the reality. So here the goal is to look at this match, at this fit using indexes. And the indexes tell us it's okay, we have a good fit. So we can go to the next step, whether we are really this common variance. Will we really this factor, which are presented here in ellipse or in circle, represent the common variance coming from the measure that are always presented in rectangles. And to do that, we have to look at the factor loadings as a contribution of each measure to actually, as of each of these measures, to the common variance to the factor. And the goal here will be to have actually high factor loadings, also high values. And what you can see here actually that we had some high values which are significant, but in most of the other cases, actually, we have only two cases. In all the other cases, here, they are pretty low and not significant. And pretty the same pattern is for the second factors. Then meaning that at the first stage that we are not really at the goal what we want to have. The other side, or the other thing to look at is what is left actually when we take into account the common, the variance which should be common across the task or across the measure. And here the goal will be to have relatively low actually values, but as you can see, it's not the case. So when taking the information together, it means that yes, we have a good fitting model, as a model that fits good the data. However, here we don't have a good factor of attentional control that represents the common variance across the task. Please note that we replicate the results from previous research when we show that we have a good model fitting, but it was a little bit of surprise that actually we didn't find this factor of attentional control representing the common variance. So in order to be sure that we have that our results are robust, we apply a multiverse analysis approach, meaning that we try using different task selection, data transformation, scoring method, structural equation modeling approaches, and trimming procedure. We apply all these possibilities and we perform the analysis again in order to see whether the results are robust, whether we are always coming to the same results. And actually, it's the case. We never had a good factor of attentional control, irrespective of how we analyze the data. And this study raised some debates in the field, why it is so difficult to find some common variance across the attentional control task. And two methodological challenges have been put forward to explain that. The first one is that actually it's really difficult to isolate attentional control from measurement error. So we know, I said it before, every measure you have some noise in the measure. And we know that for attentional control, it's really difficult to isolate attentional control, as the signal that is for us interesting, from the measurement error. And the other difficulty, actually, what we have is that most of the time we are focusing on one aspect, on one dependent variable of the task. For example, for the Stroop task, we are most of the time using the reaction time data, but we are not looking at the accuracy data or at the error rates data. And this means that perhaps we are neglecting some meaningful variance. It might be that some participants say, I want to be so accurate as possible, and then they neglect reaction time, and perhaps the variance, the meaningful variance, or the meaningful information will be on the accuracy, or reverse. So meaning that overall we are neglecting the individual differences in speed-accuracy trade-off, also in whether participants are favoring response time over time, or response time over accuracy, or accuracy over response time. And to respond to this question or to this debate, actually what we propose is to address both challenges at the same time, combining actually the hierarchical Bayesian Wiener diffusion model with structural equation modeling. Don't worry, we will go step by step again. What is first the Wiener diffusion model? So this is a model that is used actually to model decision, as a simple decision, for example, whether you see a stimulus and whether the stimulus is red or blue. It's an example for what is used. And here, the idea in this model is that you have a process, which is presented here by this line, that accumulates across time. And when this process reaches a threshold, you will produce a response. You will say, oh, it's blue, oh, it's red, okay? And in this model, you have several parameters that can be estimated. Here, I will present 4 of them. Also, you have the initial bias. You can have a bias for responding, for example, more to the red response than to the blue response, or the reverse. And you also have a parameter that estimates the non-decision time, also everything that has not to do with the decision, such as, for example, the encoding time, also the time you need to see and encode the information, but also the time you need to really press to press the button or to articulate, for example, for the Stroop task, the response. The third parameter is the boundary separation. Also here, it allows us to estimate to what extent a participant actually favor accuracy over speed or speed over accuracy. And last but not least, you have the drift rate. And here it gives us actually the quality of information processing. So, and we are expecting that for people or participants with a high ability or high attentional control ability, they will have a better drift rate or quality of information processing actually, because they can better extract relevant information from irrelevant information. Okay. And why is it interesting to use a Wiener diffusion model? Because it allows us to take into account the differences, the individual differences in speed accuracy trade-off. Because first, the diffusion model is fitted to the joint distribution of reaction time and accuracy. So we are no longer neglecting one, for example, the accuracy in the sub task. We need both the information. And the second aspect is that the diffusion model disentangle the person speed accuracy setting, whether the person is favoring speed over accuracy or accuracy over speed, from the quality of information processing on which we expect to have that attentional control has an impact. Okay? But as I said before, we didn't use simply the Wiener diffusion model. We use it in combination as a hierarchical Bayesian Wiener diffusion model, meaning that actually we are not only modeling yet the group level, but at the individual level. And which is very nice because it allows to reduce the measurement error. And then we can, for example, estimate the parameter for each individual based on the data from all other participants. So here it means we have a solution, mathematical solution, that allows us to address the two methodological challenges we have. And if really the two methodological challenge we have are the reason why we so far didn't have this common variance across two tasks, here we should expect to establish a good current factor of attentional control on the drift rate, because here we should be able to see this common variance across the measure. And here I show you the results. And here you have again the factor, also what we're expecting, the common variance. And here you have the measure, what we measure. Again, you can see we have the Stroop, and we also had two flanker tasks. Looking now at what is left, we see again that the measurement, also the measurement error was very high. And looking at the factor loading, also at the contribution actually of each measure to the common variance, we see actually that it was very low again for most, only one was very high. So here again, we don't have evidence for a good factor of attentional control that represents this common variance across the measure. Okay, meaning that when we address the two methodological challenges, it didn't help. We are not at the goal that we can find this common variance across the measure. And when I was in this situation, I say, okay, perhaps we'll to look back to the roots and to look at the original studies, and are the results from the original study robust? And when I look at the original studies, I see that attentional control was not extracted, for example, from Struber's flanker task. At the time, it was extracted from two other type of tasks. The working memory task, as said before, the task allows us to assess the temporary maintenance of information, but also to manipulate this information. So for example, when you are doing some math in your head, you have to retain the number in your head, but at the same time, if you are to add them together, you have to manipulate the information in order to have the correct response. So, and the other type of tasks are the short-term memory tasks. They are pretty the same, but the big difference between the two is that here the tasks are only used actually to measure the temporary maintenance of information. For example, you need this ability or the temporary maintenance when you have to retain for a short duration a telephone number. And they use two models to extract attentional control from this task. Here in one model, attentional control was extracted as a residual variance from working memory task. Also here you have the two types of tasks, working memory, also the measure, the working memory measure, and the short-term memory measure. And what they did first they extract the maintenance aspect, also the short-term memory aspect of all the tasks separately depending on the type of material the tasks were. So when the tasks were verbal numericals, it means, for example, it was letter and numbers, it will be do it separately from when the task use, for example, spatial materials such as matrices. And then in the first model, they extract attentional control only from the attentional control task. Okay? The second model is pretty the same, except that in this case, attentional control is not only defined by the working memory task, but also by the short-term memory task. So meaning that here, attentional control is assumed to be the common variance across both working memory and short-term memory task. And as I said before, the question was, okay, we already know that the model has a good fit to the data, but do we find the same problem in these type of model as the problem we have with the typical attentional control task? So can we here observe good factor of attentional control? And to respond to this question, we perform a systematic search of previous research. We find 3 studies on which we can apply the 2 methodology, we can apply the 2 models with enough participants. And then we reanalyze the data using the original data. But in order to be sure that the results are really robust, what we did, we simulate from the original data 5,000 further datasets as a correlation in the case, in order to see whether small variation, which can't, for example, happen if we were doing 5,000 times the experiment in different labs, if this variation have no impact on the main result, that we can always find the same results that are robust, actually. And here I presented you the result for the first study, for the first data set, and for the first model. Here you have the percentage of the model on the y-axis, and on the x-axis you have this percentage of model that fall into 4 categories. Also, you have the first category is here issues, is that when the model did not converge. For example, you didn't have a mathematical solution that match the data with the model. Then you have the second category is you have a bad fit. You have a solution, so it converged, but the fit between both was still bad. We have the third category, which we already see before, also we have a good fit, but the factor is not representing this common variance across the measure. And last but not least, we have the category we want to have. It means we have a good fit and we have a good factor that are representing common variance across the measure. And I always presented you a red line, which is the result we're using the original correlation matrix. And as you can see here, we could reproduce the results from the first study. But when looking at the robustness, also for using the simulated data, we see actually that these results were not really robust. And it was exactly the same pattern when we look at the second model. Now we have a second data set, and as you can see, for one model, we could replicate or we could find a good fit with good factor. For the other model, it was not the case, but in both cases, the results were not robust. And finally, we can use one of my data sets. And here we have for one model the same problem as before. We have a good fit, but still bad factors. And here we have only issues, actually. But in any case, we could, as the results are not robust, as we could not replicate this finding across all simulated correlation. Now, one question we can have in this context is, okay, perhaps we should choose something in the model estimation to improve it. And actually, we did that. We applied the typical model modification in order to be sure to boost the probability or the chance to finding something. The point is, even if we do that, we never find a model, a robust model showing good fit and coherent factors. Perhaps you can ask and you say, perhaps I am too strict, and perhaps I am. But the question is our approach valid? Perhaps we want too much, actually. It's something that we can achieve. And to respond to this question, actually, we applied the same approach on 3 correlation matrices and models that are well or at least better established than the one with the attentional control and the working memory task. And we applied that across 3, and as you can see, even if in one of the datasets, which is more closer to our dataset regarding the type of task and also regarding the number of participants, we can see that even if it's not perfect, we can find good fit occurring factor, and these can be robustly observed across the simulation, the simulated data. So the meaning is, yes, our approach is valid. So again, meaning that if we are yet at the point that using the typical task, we can't find some common variance across the measure. Using the original way of doing it, we can't find the common variance across the measure. We are very disappointed because it seems that we don't have what we want to have, some common variance across the measure, meaning that we are not measuring the same control processes across at least two different tasks. So coming to the main question, do we have converging evidence that several tasks measure the same attentional control process? The response is here clearly using the typical task is not the case. What does it mean? It means that we are at best measuring task-specific processes in the typical attentional control task. For example, when you are using the Stroop, you are measuring the Stroop processes. When you are using the Flanker, you are measuring the Flanker processes. But you are not measuring something that we can call attentional control. This has two consequences. First, we should stop thinking about attentional control as a diverse or heterogeneous construct, because at the moment what we are measuring is very task-specific in each case. The second consequence is, as I said at the beginning, attentional control is used as an explanatory construct in a lot of areas of psychology. But at most of the time, they are using one task in the experiment to link, for example, or to relate, for example, the different process or phenomenon of interest. But for example, when they are using the Stroop task, they are simply linking the Stroop processes or the task-specific processes related to the Stroop with the construct of interest they have. So meaning that they cannot say that they are measuring attentional control, and they cannot use attentional control to explain the relationship between two other constructs. So the conclusion of that is that we must rethink of the concept of attention control. And this is really a big question, and I am not the first one to ask that. The question is, how can we do that? And at the moment in the field, and I would say I also propose two different ways to go along with that. The first proposition is to develop better tasks. And to do that, first what we try with my PhD student was to reduce the diversity of attentional control tasks. So we took one task and always the same task, and we try to only to have different stimulus material, such as is done, for example, in other construct like working memory. But the point is, it was disappointing because the tasks that we choose have its own issues, meaning that the task was really good, adequate to reduce the diversity, but we see that the task actually is not really measuring what it should measure. So this was not the solution. So what I'm trying as well is perhaps the issue is not on the attentional control side or on the side on the trial triggering the attention control, but perhaps rather on the side on the baseline. Perhaps the congruency trial as a mixed with the incongruent trial as not the best way to extract attentional control. It is possible, for example, that you have some carryover effect when you are mixing congruent and incongruent trial rapidly across several trials. It might be that attentional control will be carried over across the next congruent trial. And then when you're talking the difference, you are removing some attentional control processes. And in one project, the idea was actually to say, okay, to take another kind of baseline, extern, also not intermixed with congruent and incongruent trial, in order to see whether we can achieve this goal to find some common value, also at least to find some variance across the measure. But at the moment, I can say nothing because the data collection is ongoing, actually. And the other way for developing better tasks, what we tried, as well as with my PhD students, is that here it was to increase the attentional control demands. So the idea actually is that perhaps in the task which are using so far, they are too easy. You don't need really attentional control, especially for a young population. So meaning that perhaps we have to increase the attentional control demand in order to have a better measurement. And we try that in two ways. First, we ask our participants to perform, for example, the Stroop task, but on some occasion, participants have to respond to the irrelevant feature. So they have no longer to respond, in the case of the Stroop task, to name the color of the word, but they have to really read the word, for example. But again, here the data collection is ongoing at the Vinzenz Pallotti University, so I can't say nothing so far. What we also try here and the data collection was ongoing here at the Vinzenz Pallotti University, was to combine the attentional control tasks together. And this perhaps it was the beginning of the talk, you should remember, I already tried that in the experimental way, but here was the goal to use it in an experimental correlative way. And to do that, we take the paradigm as we had before by combining Stroop and Flanker together, but not only Stroop and Flanker, but with other tasks, for example, the Simon task. And then to look whether this double paradigm, as a Stroop Flanker, will correlate with Stroop Simon or with Flanker Simon, for example. And so to look at the common variants, we will here compute a correlation. But to do that, we decide also to use a hierarchical Bayesian linear modeling approach because they allow us to better isolate attentional control from measurement error. And here I can briefly presenting you the results. We have two studies. Here I presented you the first study or the first experiment. On the y-axis, you have actually the two paradigms that were combined together. And so here, for example, the Stroop-Flanker paradigm was correlated with the Flanker-Simon. The Stroop-Flanker was correlated with Stroop-Simon, and the Flanker-Simon paradigm was correlated with the Stroop-Simon paradigm. And on the x-axis, it's the correlation magnitude, and the red line is actually the correlation, the typical correlation value using the previous task, using the typical task. And as you can see here, we have the correlation, and you have the credibility interval, and you have the posterior, and here you can see that actually looking at the point, which is the mean, actually the mean correlation, here you can see that we have better correlation actually than the typical one. However, and there is always an however, one aspect is that we have overlapping feature. So for example, all the tasks participants were asked to perform a color decision. And this might perhaps explain why we find so high correlation. So in the second study, what we did, we again use this double conflict paradigm, but this time actually what we did, we have no overlapping feature across the task. And as you can see here, actually the common variance, which is shown here by the correlation, is no longer better than the typical task. So for the moment, it seems that increasing the attentional control by combining the task is not a solution to have a better measurement. I said before, one proposition is to develop better tasks, but one way perhaps to develop better tasks is to have better theory of attentional control. And here, one way to help in this direction is to use formal cognitive modeling. So what is that? Formal models of cognition actually help us to translate a verbal theory, what we have most of the time in psychology, into a set of equations, of mathematical equations. And the idea is that this equation reflects the theoretical assumption that we have about the cognitive processes, for example, attentional control, that generates the behavior. And the idea that so far the model are done or model at the group level, but they are not taking into account individual differences. And we should integrate this model in order to take these individual differences in order to integrate them into the experimental correlational approach in order to find a better measurement of attentional control. So meaning that at the end, I should add more approaches in my research, something like an experimental modeling correlational approach with the hope that finally we can find a good measurement of attentional control. So you see how exciting the time is actually, because we are really try a lot of things and know we have a lot of possibility opening up. But for me, today I am coming to the end. I have to thank a lot of people. First, all my co-authors and collaborators that helped me in the different projects. I have to thank all the students and participants who took part in the project in one way or another. And I have to thank the different research funding organizations that helped to finance the different projects. And last but not least, I have to thank you for your attention.